All right, 5.3. So you should have watched the 5.4 lecture video before watching this one. So if you haven't watched 5.4 yet, go back and watch 5.4 first, and then you can come back and watch this one. 5.4 talks about the multiplication rule for computing the probability of E and F just in general. In 5.3, we're going to talk more specifically about the multiplication rule for independent events. So let's start off by defining what we mean by independent events. So two events E and F are independent if the occurrence of event E does not affect the probability that event F occurs. And then E and F are dependent if they're not independent, right? So if E affects F or if F affects E, then they are dependent events. So let's just practice identifying whether events are independent or dependent. So part A says draw a card from a standard 52 card deck of cards and then roll a die. I guess those aren't really events. The event would be like drawing a king from a deck of cards and then rolling a 2 or something. But clearly the events are independent there, right? They have nothing to do with one another. They have no effect on each other. Part B says draw a card from a standard 52 card deck of cards and then draw a second card from the same deck without replacing the first card. And that would be dependent, okay? Because let's say that the events you're looking at are drawing kings again. So the probability you draw a king the first time is going to be 4 out of 52 because there are 4 kings in the deck and 52 cards in the deck in total, so 4 out of 52. But now once you've drawn that king, if you don't put it back in the deck, then there are only 3 kings left in the deck and only 51 cards left to choose from. So the second time you draw a card, the probability that the event occurred has changed, right, based on the first event occurring. So those are dependent events for sure. Part C, draw a card from a standard 52 card deck of cards, then place it back in the deck and randomly draw another card. Okay, those would be independent events for sure. Okay, right? Because the probability that you draw a king on the second card has nothing to do with the probability of drawing a king on the first card, since you placed the card back in the deck and shuffled the cards again and all of that stuff. So anyway, part D says, suppose 2 40-year-old women who live in the United States are randomly selected. The events woman 1 survives the year and woman 2 survives the year. This particular section, for some reason, has a lot of examples in it that are pretty morbid. So anyway, so you just have to bear with me. But anyway, so the events woman 1 survives the year and woman 2 survives the year. These would be independent events. The first woman living or dying has no bearing on whether or not the second woman is going to live or die, right? They're independent of one another. Unless maybe it's like the first woman crashes her car into the other woman or something like that, right? But no, they're independent events. Okay, part E, the events earn a bachelor's degree and earn more than $100,000 per year. Okay, those would be dependent events. And that's oftentimes, I've found, kind of a controversial thing for students to hear for some reason. But I think the reason that it's controversial is because you think, well, but I know a lot of people who don't have a bachelor's degree who make more than $100,000 per year. So you don't have to have a bachelor's degree in order to do well in life. And that's absolutely true, okay? But that's not what we're saying either when we say that the events are dependent. We're not saying that you have to have a bachelor's degree in order to earn more than $100,000 per year, nor are we saying that if you have a bachelor's degree, you're guaranteed to earn $100,000 per year. What we are saying is that if you have a bachelor's degree, you're more likely to earn more than $100,000 per year than you would be if you didn't have a bachelor's degree. And that is true, right? Those are dependent events. Okay, now, if E and F are independent, then the probability of E given F would be equal to the probability of E, right? Because if F has no bearing whatsoever on whether or not E occurs, then probability of E given F is just the same thing as the probability of E, right? F doesn't affect whether or not E occurs. Similarly, probability of F given E would just be exactly the same as the probability of F. So with that in mind, if you recall the general multiplication rule from 5.4, right, we saw that probability of E and F was probability of E times probability of F given E. But if E and F are independent, then probability of F given E is just the same thing as the probability of F. And so we have a slightly easier formula to use if we have independent events. So if E and F are independent, then probability of E and F is probability of E times probability of F. Okay, and so this is called the multiplication rule for independent events. So let's look at this rule in action. And just keep in mind as we look at these examples that this rule is only usable if in fact the events you're looking at are independent. If they're not independent, then you have to use the general multiplication rule that we talked about in 5.4. Okay, but this test, or this example says a test has two questions, a true or false question and a multiple choice question with 5 possible answers. The student completely guesses on both questions. Now, part A asks, is it reasonable to assume that the events got the true or false correct and got the multiple choice correct are independent? And the answer is yes, right? This student is completely guessing on both questions. So it's completely independent whether or not she gets the first one and the second one correct. So yeah, those are independent events. Now, part B says, compute the probability that the true or false question is correct. Well, for the true-false question, there are 2 possibilities, true or false, and the student gets 1 guess. So the probability they get it right is 1 out of 2, or in other words, 50%, right? The probability they get the multiple choice question correct. Now, this particular multiple choice question has 5 possible answers. So there are 5 possibilities, and again, the student only gets 1 choice. So there's a 1 in 5 chance that they're going to get the multiple choice question correct. That's 20%. So now part D asks, what's the probability that they get both questions correct? And probability they get both correct is the probability that they get the true false correct times the probability that they get the multiple choice correct. Okay? And that's what the multiplication rule for independent events says, right? So that you can just multiply those 2 things together. That's pretty good. That means if this student just guesses, there's a 10% chance they're going to get 100% on this particular test, which isn't bad. Of course, that also implies that there's a 90% chance they're going to fail. So maybe the student should study. But that's that. Let's look at another problem. This one says a survey of 10,000 African Americans found that 27 had sickle cell anemia. Suppose we randomly select one of the 10,000 African Americans surveyed. What's the probability that he or she has sickle cell anemia? Probability they have sickle cell anemia. Well, 27 of the people surveyed had sickle cell anemia. So the probability you choose someone with sickle cell anemia is going to be 27. There are 27 ways to choose someone with sickle cell anemia out of 10,000 people to choose from. So the probability the person has sickle cell anemia, 27 out of 10,000. Which as a decimal, we would just move the decimal place 4 times, 0.0027, right? Now part B says if 2 individuals from this group are randomly selected, what is the probability that both have sickle cell anemia? So the probability they both have sickle cell anemia, I'm going to label this as follows. I'm going to say this is the probability the first one has sickle cell and that the second one has sickle cell. And these are not independent events because once you choose the first person, you're not going to put them back into the pool of people to choose from again, right? So the probability for the second person is going to be different based on what happens with the first person. So these are not independent events. We would say this is going to be the probability the first one has sickle cell times the probability that the second one has sickle cell, given that the first one did. The probability that the first person has sickle cell is 27 out of 10,000, just like we saw in part A. But now, if you assume that you've chosen somebody already from these 10,000 people who has sickle cell anemia, then the probability you're going to draw another person with sickle cell anemia is now 26 out of 9,999, right? Because you already chose a person with sickle cell, and so there are only 26 people left who have sickle cell anemia, and there are only 9,999 people left to choose from. So let's see what we get here. Something really small, I'm guessing. 27 out of 10,000 times 26 out of 9,999 is so that's about 0.00000702. So 1, 2, 3, 4, 5 zeros, and then 702. Now, part C asks us to do something that may seem a little bit strange at first, but you'll see why. It says, compute the probability of randomly selecting 2 individuals from this group who have sickle cell anemia, assuming independence. So if we assume that the events are independent, which they're not, okay, but if we assume that they are, then the way we would compute this probability is we would just say, well, this is the probability that the first one has sickle cell times the probability that the second one has sickle cell. And if we're assuming independence, right, if we're assuming independence, then this is going to be 27 out of 10,000 times 27 out of 10,000. Okay, we're assuming independence, right? So 27 out of 10,000 squared. That's about 0.00000729. So 5 zeros and then a 729. What I want to point out about this is that while these two numbers are not exactly the same, they're pretty darn close. If you round to 4 decimal places, they're both 0, right? If you round to 6 decimal places, they're both 0.000007. So they're really close to each other, even though they're not exactly the same. And what that tells us is that even when you have events that are not independent, you can still use the multiplication rule for independent events as long as you have as long as your sample size is small. Let me say it again. As long as your sample size is small compared to your population size, right? So if your sample size is much, much smaller than your population size, then you're free to use the multiplication rule for independent events, even if the events are not actually independent. And the reason this is nice is because the multiplication rule for independent events is a lot easier to use than the general multiplication rule is. So let's look at some more examples so you can see how useful this is. Here's another really morbid one, right? So it says the probability that a randomly selected female aged 60 years old will survive the year is 99.186%. What's the probability that 2 randomly selected 60-year-old females will survive the year? Well, listen, my mom is 63 years old, so and your life expectancy doesn't improve as you get older, right? So, but this is good news, right? So almost all of these 60-year-old women are going to survive the year. But the question is, if you get 2 of them, now what's the probability they both survive the year? So the probability they both survive is going to be the probability that the first one survives times the probability that the second one survives. So I'm just going to square that, right? Because, you know, there are a lot of 60-year-old women, and the sample size here is only 2. So our sample size is small compared to our population size. We're free to assume independence, even if the events are not independent. We'll assume independence. And so then we've got 0.99186 squared comes out to about 0.9837, 1, 2, 3, 4, 5, 9, we'll say. So that's pretty good. There's a pretty good odds that both of those women are going to survive the year. Although you see that it did decrease, which should also make sense, right? If one of them has a 99% chance of surviving, then there's like a 98% chance that both of them will survive. Let's do another one. Number 5 says a Harris poll found that 46% of Americans say they suffer great stress at least once a week. If 3 people are selected at random, find the probability that all 3 will say that they suffer great stress at least once a week. So we want the probability that all 3 are stressed out. Well, that's going to be the probability that the first one is stressed out times the probability the second one is times the probability that the third one is. So it's just going to be 0.46 times 0.46 times 0.46. Or in other words, 0.46 cubed. And that comes out to about 0.0973. So if there's a 46% chance that someone is stressed out, then there's like a 9.7% chance that 3 randomly selected people are all stressed out. Okay. So that's that. Now, let me give you a taste for where this might be useful for us when we're looking at data and when we're trying to extrapolate based on data that we've collected. So number 6 says, a geneticist developed a procedure for increasing the likelihood of female babies. In an initial test, 20 couples used the method, and the results consist of 20 females among 20 babies. That's pretty crazy, right? 20. So in other words, all 20 pregnancies ended up with the babies that were produced were female. Okay, that's pretty unlikely to happen, I would think, if the procedure doesn't do anything, right? Anyway, so it says, assuming that the gender selection procedure has no effect, find the probability of getting 20 females among 20 babies by chance. Okay, so we'll do that. And then it says, does the resulting probability provide strong evidence to support the geneticist's claim that the procedure is effective? In other words, this geneticist has developed this procedure that will select for female babies, right? So they'll make it so that if you get pregnant, that you're gonna get pregnant with a girl, right? And the evidence that this geneticist has to say that the procedure is effective is that 20 out of 20 couples who tried it ended up with female babies. So what we want to do is use that data to say whether or not we can say that the procedure really is effective, or is it maybe just due to some random chance that occurred, right? So let's see, let's do it. So we want to compute the probability of getting 20 females among 20 babies just by chance. So the probability we get 20 females. Well, the probability that any given pregnancy is going to be a girl is 50%, right? So and then that's the probability that one pregnancy is going to result in a girl. So the probability that 20 pregnancies result in 20 girls is going to be that number to the 20th power. And let's see how much that is. 0.5 to the 20th. So that number is so big, my calculator is giving me an answer in scientific notation. Or sorry, not big, but small. So so what this means, in case your calculator is also giving you something like this, the E here stands for, I think it stands for exponent, but what this means is 9.53674 times 10 to the negative 7. So to change that into like a number written in standard form, you would take the decimal place and move it 7 places to the left, which means that, I move it once and then I'm going to have to move it 6 more times. So I'm going to have point and then 6 zeros and then the rest of the digits, right? So this is about 0.1, 2, 3, 4, 5, 6 zeros, and then 9, 5, 3, 7, you know, ish. That's really small. That's very, very unlikely to happen by chance. And yet, it did happen here. So what does that tell us? That tells us that the procedure is most likely the cause of the 20 females among the 20 pregnancies, right? So most likely the procedure is effective. So does the resulting probability provide strong evidence to support the geneticist's claim? So yes. This gives us strong evidence that the procedure is effective. Okay, and if you want to write down more than what I'm saying, that would probably be a good thing, right? When you come back to your notes and you're like, wait, why does getting this probability sort of suggest that there's strong evidence the procedure is effective? Well, again, it's because the probability that we would have gotten 20 females among 20 babies is so small, and yet it happened when they applied this procedure. And so that tells us that probably the procedure is what made this occur, right? So the procedure is effective. Okay, so all of these things, I think, especially numbers 4 and 5, I think that those are fairly straightforward, but some of these problems can get pretty nasty. Before we go on and look at some of the more challenging ones, I just want to remind you about the complement rule and tell you about this phrase "at least," right? So probabilities involving the phrase "at least" typically use the complement rule, and that's especially true if they use the phrase "at least one." And we'll talk about why in a second. But just note that "at least" means greater than or equal to. So, you know, if you have to be at least 17 years old to buy tickets to an R-rated movie, then that means you need to be greater than or equal to 17 years old. I'm running out of space, so I'm just going to abbreviate like that. Greater than or equal to 17 years old. You have to be 17 or older, right, in order to buy the tickets. So that's what "at least" means. It means that number or more. Okay. So let's look at let's look at what that has to do with the complement rule, which we talked about in 5.2. Okay, so number 7 says the probability that a randomly selected female aged 60 years old will survive the year is 99.186%. Okay, so back to these 60-year-old females dying. Well, anyway, what's the probability that at least one of 500 randomly selected 60-year-old females will die during the course of the year? Okay. So let's do this. Here's the phrase "at least one." At least one. Whenever you see that phrase, use the complement rule. Okay, so the probability that at least one dies, well, let's think about that. At least one of the 500. That means that we're looking at the probability that exactly one dies, or that exactly two die, or that exactly three die, or that exactly 4 or 5 or 6, all the way up to 500. Okay. If we were to do that using the addition rule, because those are all or probabilities, they would all turn into additions, we'd have to sit here and compute 500 probabilities and then add them up, and we'd be here all day doing that problem. So rather than do that, let's use the complement rule. The complement of at least one is none, right? So to make it maybe a little bit easier to visualize, let's just say that you had 5 individuals, 1, 2, 3, or maybe it would be better not to number them. A, B, C, D, E. Let's say that these are 5 individuals, and you want to know what's the probability that at least one of them has some characteristic. Well, at least one would be 1 or more. So it would be 1 or more. The complement of that happening is that none of them have the characteristic. I don't know why I wrote this out. It's probably not super helpful. But that's the idea, right? So the complement of at least one is none. So using the complement rule, right, we're going to say this is 1 minus the probability that none of them die. Another way to say that none of them die is to say that they all survive, right? So this is really like saying 1 minus the probability that they all survive. And the probability that they all survive is the probability that one of them survives, 0.99186, to the 500th power. Okay? So getting from this step to this step is just logic, right? It's just think through it, right? If none of them die, that means that they all survive. So that's just logic. But getting from this step to this step, that's the complement rule, right? That's the complement rule. Remember, complement rule says that probability of E complement is 1 minus the probability of E. So we're just using 1 minus the probability of the complement. The complement of at least one is none. The probability that at least one of the people has some characteristic, that's the complement of the event that none of the people have that characteristic, okay? So try to make that make sense in your mind. Okay, but that's that probability. Let's see what we get. So 0.99186 to the 500 is a tiny, well, it's like, so I'll say this is about 1 minus 0.0168. And that comes out to 0.9832. Okay. So this is the probability that at least one of them dies. So if you randomly select 560-year-old women, there's like a 98% chance that at least one of them is not going to make it to the end of the year, which is really kind of a sad thought. The good news is that, there's like a 99% chance that if you choose one of them, there's a 99% chance that she's going to make it. But it's just if you take 500 of them, then it's almost certain that at least one of them is not going to make it to the end of the year. Anyway, so that's that example. One thing that I'll say, just as a kind of a general warning, is that be careful with order of operations. If you punch this into your calculator as 1 minus 0.99186 and then hit enter and then raise that to the 500th power, you're going to get the wrong answer because you don't do subtraction first. You do exponents first, right? So use correct order of operations. Do the exponent first and then subtract. Okay, one more set of examples. So it says, among 21 to 25-year-olds, 29% say they have driven while under the influence of alcohol. Suppose that 3 21 to 25-year-olds are selected at random. Part A asks, what's the probability that all 3 have driven under the influence of alcohol? So we want the probability that all 3 have driven under the influence. Well, there's a 29% chance that one of them has. So the probability that all 3 have is 0.29 to the third, which is 0.024. Well, if we round to 3 decimal places, this is 0.024. Part B, what's the probability that at least one has not driven while under the influence of alcohol? So we want the probability that at least one has not driven under the influence. Well, there's that phrase again, at least one. The complement of at least one is none. So this is 1 minus the probability that none of them have not driven under the influence. And there we have this weird double negative. But if you're saying that none of them have not driven under the influence, then that's the same thing as saying that all three of them have driven under the influence. So this is 1 minus the probability that all three have driven under the influence. And that happens to be the probability that we computed in part A, right? So that's approximately 1 minus 0.024. Okay, so there's like almost a 98% chance that at least one of them has never driven under the influence of alcohol, which is encouraging, right? That's good. It's much better than the 29%. Guys, don't drink and drive. Don't be idiots. But anyway, if you randomly select 3 21 to 25-year-olds, there's like a 98% chance that at least one of them has never driven under the influence, which is good. That's encouraging. Now, part C says, what's the probability that none of the three has driven while under the influence of alcohol? So the probability that none of them have driven under the influence. Well, if 29% of 21 to 25-year-olds have driven under the influence, then that means 71% of 21 to 25-year-olds have not driven under the influence. So the probability that none of the three have driven under the influence is going to be 71% to the third power. Okay, so there's that one. And then part D. What is the probability that at least one has driven while under the influence of alcohol? So we want the probability that at least one has driven under the influence. Again, we have that phrase, at least one. The complement is none. So it's 1 minus the probability that none have driven under the influence. Well, that just so happens to be what we did in part C, right? So that's going to be approximately 1 minus 0.358. That's 0.642. Okay, this one's a little bit sadder, right? It's like if you randomly select 3 21 to 25-year-olds, there's like a 64% chance that at least one of them has driven under the influence of alcohol, which is horrible. Guys, like I said, don't drink and drive. Anyway, that does it for that example. Now, I know that this last example was something of a, if your head is spinning at this point, that's normal, okay? It just takes some practice to get used to these concepts. So if you're really confused by this, my advice would be rewind the video and rewatch it, okay? Try to do your best to understand these problems. Okay, but that's that. There's your homework assignment. And we'll see you in 5.5.